All right, everyone, it's Mr. Edie back with yet another video. So today, guys, we're going to talk about topic 2, which is rate law. So let's consider A will produce some amount of products, and as long as the rate of the reverse reaction occurs and negligibly slow, the relationship between the rate of reaction and the concentration of the reactants can be expressed in a rate law. So a rate law is equal to the rate constant K times the concentration of our reactants, in this case A, raised to the n power. Okay, so where K is the rate constant and N is what we call the reaction order. So guys, obviously you saw from the previous slide, when we're writing rate laws, we're going to be working with exponents. So I just want to review some points from math that's going to help our lives easier in chemistry. So the first thing is remember the inverse function of an exponential function is a logarithmic function. Okay, so in order to solve for an exponent, we would take the log on both sides of the equation. Next is remember that x to the n power divided by y to the n power can be simplified as x divided by y raised to the n power. Okay, that's going to help us tremendously when we want to solve for the exponent n. Okay, now if we have the log of x to the n power, we can rewrite that to n times the log of x. Okay, anything to the 0 power is 1, and then anything raised to the first power is itself. Okay, so these 5 bullet points, guys, are going to help us moving forward, particularly when we're solving for our reaction orders. Okay, so this is going to help us quite a bit. So I just wanted to make sure we were all on the same page as I am. And again, Mr. We've been saying this a lot in class that you've been learning things in math class, and well, where do you use them in real life? Well, we use them in chemistry. So all those rules that you had to learn about exponents in math, we use them in chemistry. So keep that in mind as we're solving for reaction orders. So the reaction order is simply dependent upon the concentration of the reactant. Okay, we can have if n is equal to 0, the reaction is 0 order, and the rate is independent to the concentration of A. If n equals 1, the reaction is first order, and the rate is directly proportional to the concentration of A. Okay. If n equals 2, the reaction is second order, and the rate is proportional to the square of concentration of A. So let's say what this looks like in terms of a graph. So this slide here, guys, is comparing 0, first, and second order reactions. I'm going to go and explain each graph more particular, but here's a great image just comparing the differences between them. The blue graphs, guys, are concentration versus time, and then the orange graphs is rate versus concentration. Okay, so in terms of what we were talking about, the rate from the previous slide, you'll notice here that the rate is constant, okay, in a 0 order reaction. Here, the rate is directly proportional to the concentration of A. And then here, the rate is proportional to the square of A. So if you look, constant, linear relationship, and finally a quadratic relationship. We're going to explore this more in depth on each individual slide now. Okay, so let's talk about 0 order reactions. As I said before, the rate of reaction is independent of the rate of the reactant. Okay, so the rate would equal the reaction constant K times the concentration of A to the 0 power. Well, anything raised to the 0 power is 1. So the rate of a 0 order reaction is simply the rate constant. Okay. Now, if we're looking at concentration of A versus time, we would see a linear decline. So that's this blue graph here. So concentration versus time. As time continues or the reaction proceeds, the concentration of A would decrease in a linear fashion. If we're looking at rate versus concentration, though, the rate is unaffected by the concentration of A. So as you see, the rate here is the same no matter what the concentration of A is. Okay, so it's constant. Okay, so when do zero order reactions occur? They would occur when the reaction available, they would occur where the amount of the reactant actually available for the reaction is unaffected by the changes in the overall quantity of the reactant. So this would be like in sublimation, guys. Only the sublimation of dry ice. So only the dry ice that is exposed on the surface will sublimate and form, obviously, CO2 gas. So that it doesn't matter how much dry ice I have in that standpoint, because only the stuff available to the surface is going to sublimate. So therefore, that would be a zero order process. Okay. Let's talk about first order now. So first order is directly proportional to the concentration of reactant A. So the rate would equal K times the concentration of A raised to the first power. Okay. The rate slows down as the reaction proceeds because the concentration of the reactant decreases. Okay. So in this case, concentration versus time, you'll notice that the slope decreases. So it starts pretty steep here and then it kind of bellows out towards the bottom. Again, that's because if we were looking at the rate versus the concentration, it's a linear relationship because it's directly proportional. So the rate is directly proportional to how much concentration is there. Okay. Second order reactions, the rate is proportional to the square of the concentration of the reactant. So in this case, the rate would equal the rate constant K times the concentration of A raised to the second power. So the rate is even more sensitive to the reactant concentration. So if you guys are looking at concentration versus the time graph, that slope quickly flattens. Where when we look at the rate versus concentration, the slope is a function of concentration of A, which is a simply fancy way of saying that it's quadratic, right? This would be one side of a parabola if I actually graph the whole parabola here, but as you can see, it's going up and it starts to go steeper as we have more reactant. Okay. Now, when we want to determine the order of a reaction, we can, first off, it can only be done through an experiment. So, in other words, we need experimental data. Okay. So, without experimental data, folks, we can't determine the order of a reactant. Now, the other thing that we can't determine without a reaction then is the rate constant. So in order to find the rate constant, we need to determine the order of reaction. And in order to determine the order of reaction, we have to use a experiment. So obviously we have the experiment here. We did some experiment with reactant A and it gave us these numbers. And using the data, we're going to determine one, the order of the reaction, and then two, the rate constant. Okay. We can do a couple of ways. We can get this by two ways. There are two ways to solve for the reaction order, but let's start off by simply writing down what the rate law would be. So the rate law is going to be rate is equal to the rate constant K times the concentration of A raised to some power N. Okay. Now, you'll notice, guys, that the first bullet here wants us to find the reaction order, or N in this case, right? So remember, N is the reaction order, and we can't find K without first finding the reaction order, okay? So if you guys take a look here, it says we can use the method of initial rates, right? So that's what it says here. And I'm going to show you this method right now. So in order to use initial rates, we obviously need data. As I said before, you need experimental data in order to do anything involving kinetics. Okay, so particularly rates of reaction and then the rate law. So we have the initial rate and we have the concentration of A, right? So now I can say, okay, well, what happened between 0.1 and 0.2 to the rate, right? So it started out 0.015 and then it doubled. So I'm going to say, okay, this was times 2. I'm going to do the same thing on the other side. So 0.1 to 0.2 is obviously, again, times 2. Okay. And then it doubled again for both of them. Now, since both of these are doubling every time I look at, like, okay, so concentration of A, it doubled, and then the rate doubled. And then the concentration of A doubles from 0.2 to 0.40 here, the rate doubled again. Well, if that's the case, if it keeps doubling like that, then our relationship is obviously directly proportional. So if I have a directly proportional relationship here, right, if I have something that's directly proportional, that means my reaction order, N, is equal to 1. So this reaction is first order. Again, how do I know? Well, when my concentration doubled, my rate doubled. And that happened in both times I increased the concentration of A. So when I went from 0.1 to 0.2, it doubled. 0.2 to 0.4, that doubled, and the rate doubled with respect to that. So if that's the case, it's directly proportional. That means N is equal to 1, right? Now, I can say, okay, well, my rate is equal to the rate constant K times A raised to the first power. Okay, well, now I can solve for K and solve for number 2, right? Now we're going to do number 2, which is to find, and this, by the way, was all number 1, but now I can do number 2 and solve for K. So the reaction constant K is going to be the rate divided by the concentration of A raised to the first power. So I'm going to pick any trial, guys. And when you pick a trial or a run, make sure you use both sets of numbers. So I'm going to use run 1. So I'm going to use the initial rate of 0.015 divided by the concentration at 0.1. Okay. So make sure your numbers are consistent for the same trial or run. And I'm going to do 0.015 molar seconds. And folks, it's super, super important that you have your units written now, because the rate constant K in kinetics changes dependent upon the reaction order. So keep that in mind. And then we're going to have concentration A, 0.1 raised to the first power. Don't forget the molar, like I just did. The units for concentration is molar. And when I plug this into my calculator, I get 0.15 per seconds. And that is the rate constant K. So the rate constant K is 0.15 per seconds. Another way to write per seconds is to do S to the negative 1 power. And I am good to go. I have done everything for this reaction. Okay. Well, I'm sorry. I'm not for this reaction. I have determined the overall order of reaction, and then I have found the rate constant. So that's what you would do. Let's move on to another example. All right. So this one says, the rate of reaction can be determined only by experiment. We already know that. We can use the method of initial rates, which I'm going to use for reaction 1. And then I'm going to show you the equation method, which is the rate 2 over rate 1 is equal to K times the concentration of A at some point at rate 2 to the raised to the n power divided by K times the concentration of A at rate 1 to the n power. So it will make more sense when I do that, but I just want to show you the other method. Okay, so we've been tasked with determining the reaction order for each reaction. So let's start with reaction 1. Okay, well, here we are doubling our concentration again for both of these. Okay, in reaction 1, we doubled our concentration, but you'll notice the rate is constant every time I double my concentration. Well, since it's double, guys, reaction 1 is 0 order. So that was pretty easy to see. Reaction 2, I could do the same thing. I could use the method of initial rates, or I could do this equation here, as I tried to read earlier to you. And since I've shown you the initial rates method 2 times, guys, I am now going to show you how you would use this expression in order to solve for the rate. Okay, so let's dive into this. So I'm going to do on this equation here, guys, I'm going to do trials 1 and 2 when I'm doing my math. So here we go. We've got rate 2 over rate 1 is equal to K times the concentration of A at rate 2 time. I'm just going to write the whole expression, guys. Bear with me here. All right. So you'll notice that they're raised to the n power, and I have the concentration of A at rate 2 here, and the concentration of A at rate 1 here. Okay. Now let's simplify this expression because I can simplify it. The K's are going to cancel out because they're both in the numerator and the denominator. Okay. And then what I can also do is if I rewrite this, so I do rate 2 equals rate 1, I can put the concentration of A at rate 2 on top over the concentration of A at rate 1 on the bottom. And since it's the same exponent, I can rewrite this expression with putting the n on the outside. All right, so I took the n that was, in the numerator and the denominator, and I put everything in parentheses to put the n over there. Okay, so that's where those tricks of exponents are coming in. And now, guys, I'm going to plug in some of my numbers. Okay, so I'm going to plug in. So like I said, I'm going to do trial 2 and trial 1 here. So I'm going to plug in 0.060 molar seconds divided by 0.015 molar seconds, okay, is equal to the concentration of A, which is going to be 0.2 molar, divided by the concentration of A at rate 1, so 0.1 molar, raised to the n power. Guys, you'll notice real quick before I continue anything, my units are all going to cancel out. Now, this does make sense because I'm looking for an exponent. So it makes sense that the units cancel out because exponents aren't going to have a unit to them. And now I'm going to simplify my numbers here by just dividing them out. Okay, so when I do that, I get 4 is equal to 2 to the n power. Now I'm going to take the log of both sides in order to solve for n. So the log of 4 is equal to the log of 2 to the n power. Now using my trick with exponents, I'm going to rewrite this as the log of 4 is equal to the n times the log of 2. All right, don't forget my extra 0 there. Okay, and now I can say, okay, well, n is equal to the log of 4 divided by the log of 2. And that will make my n is equal to 2. So this reaction reaction 2 is second order. Now, guys, truthfully, what preference do I have when I am doing these problems? If it's easy to, like, for me, it's very easy to see when I have a reaction in first order or a reaction in zero order. Again, in zero order, the rate is going to be constant with respect to the concentration. So the rate remain the same with respect to the concentration of A. Okay, where when we're looking at a first order reaction, as you saw on the previous slide, the rate was directly proportional to the concentration of A. So every time concentration A doubled on the previous slide, you saw that the rate doubled as well. Now, second order reactions are a little bit trickier for me to see, but nonetheless, you could do the method that we did before, right? You could still do initial rates. So you can say, okay, well, From here to here, we have times 2. From here to here, we have times 2. 0.015 to 0.060, it quadrupled, and then it quadrupled again. Okay, so this is indicating that it's proportional to the square of of this, but it's harder for me to see that personally in a data table. So if I don't see a zero order reaction or a first order reaction, I usually prefer this method here, where you pick two of the rates, set them equal to two of the concentrations with their rates, and then solve for the exponent. Okay. Either way is fine for me. Math is very personal. So if you're able to see second order reactions, you're absolutely free to do so using the initial rates method. All right, let's continue. So let's talk about the reaction order of multiple reactants. So as you can see now, we have AA plus BB yields CC plus DD. Okay. So again, as long as the reverse reaction, is negligibly slow, the rate law is proportional to the concentration of A to the M power multiplied by the concentration of B raised to the N power. So that's how I would express my rate law. So rate law equals K times the concentration of A to the M times the concentration of B to the N power. Okay. So in order to find the overall reaction order of this particular reaction, I would just simply add the exponents together. So I would add M plus N. So let's say if I had, in this case, M was first order and N was second order, then the overall reaction order for this particular reaction would be then 3. Okay, so that's all that is. Very simple. Super important. Rate laws can only be determined experimentally, right? And that's kind of the common theme that we're seeing in this unit. Again, it has to be determined in the experiment. So it doesn't matter if we're looking at a simple rate law when it's just one reactant or a reaction with multiple reactants. Again, we have to look at this experimentally. Okay. And now, when you have more than one reactant, you're going to find the order of one reactant when the other one is being held constant. And what do I mean by that? I'll show you on the next slide. Okay, our final slide of the day, which is consider the reaction between nitrogen dioxide and carbon monoxide. So NO2 plus CO yields NO plus CO2. The initial rate of the reaction is measured at several different concentrations of the reactants, and it is tabulated, and the results are shown here. From the data, determine the rate law for this particular chemical reaction and the rate constant K for the reaction. All right, everyone, sorry about that, but in order for me to have enough space to obviously solve this problem with you, I had to edit out those directions. But now that you have those written in your notebook, we should be able to dive right in. So guys, as I said on the previous slide, when we have two reactants, right, in order for us to find the reaction order of one, we're going to have to take advantage of when the other is being held constant. Okay, so that's the strategy we're going to take advantage of when we're doing this. But just as remember, for a rate law is the expression here. So rate is equal to K times the concentration of nitrogen dioxide raised to some power N times the concentration of CO, carbon monoxide, raised to some power N. Now, in order for us to have this rate law completely written, we have to solve for M and N. So solve for the exponents. Okay, so that's what we need. Now, as I said before, we can do one of two methods. We can use the initial rate method by just examining the data in the table, or we can use, the rate 2 over rate 1 is equal to the concentration, and we'll say, I'm going to write this for NO2 for us. Okay, so NO2 at some point 2 to the M power over the concentration of NO2 at the first rate, again, raised to the M power. So I can use this way, or I can evaluate the data table. So let's dive right into this. I think I'm going to do carbon monoxide first using the initial rates method, and then I'm going to worry about NO2 later. Okay, so let's do CO first. Okay, and we're going to do CO2 or CO, carbon monoxide, be at trial 2 and trial 3. Now, the reason why I'm going to do them carbon monoxide at trials 2 and 3, everybody, is because that's when NO2 is being held constant. So if you take a look at NO2, it's held constant here, right? So it's 0.2 to 0.2. This is a good place now to examine the rate of carbon monoxide, because we know NO2 will have no effect on this. Okay, so we're going to look at carbon monoxide here. And if we take a look here, carbon monoxide from trial 2 to trial 3 is going up, the concentration doubled, right? So the concentration of carbon monoxide doubled here, okay? However, the rate is constant. So since the rate is constant here, right? So the rate is constant. We know that the constant, so like, since the rate is constant, right? That means N is zero order. So the concentration of carbon monoxide is zero order, which means that's effectively 1. Okay. That's good to know. It's going to make our lives easier. Now I'm going to pick either, now in order for me to find the M, right? In order for me to find exponent M, I could do one of two things. I can look at trial 1 and trial 2, because that's when the concentration of CO is changing. And actually, that's the one that I'm going to use. So again, since I'm finding M right now, right? So I'm finding exponent M, I'm going to look at trials 1 and trial 2, because that's where the concentration of carbon monoxide is being held constant. Okay, so let's do that, trial 1 and trial 2, so we can find the concentration of NO2. So when I do this, we're going to do 0.0082 divided by 0.0021. This is molar seconds. Okay, molar seconds here is equal to the concentration of NO2 at trial 2. So that's 0.2. One thing to keep in mind, I forgot to write this before, but our K's here are still there. But as we know, those K's are going to cancel out. And then I'm going to, for the sake of making this easier for myself, I'm going to put the M on the outside. All right. So I'll show you what I mean by that in just a moment. But the concentration at rate 1 here. And then I'm going to raise this to the M power, just to keep things simple. Remember, because I didn't, that this is concentration. So these units are molarity. And as I said before, when we're looking for an exponent, all of our units cancel out. So I'll cancel those out. And now I'm going to simplify the numbers. So when I simplify the numbers, I get 3.9 is equal to 2 to the M power. Now I'm going to take the log of both sides. So we get the log of 3.9 is equal to the log of 2 to the M. Rewrite my exponent so I can do this. So log 3.9 is equal to M times the log of 2. So now I can say, okay, well, M is equal to log of 3.9 divided by the log of 2. M is going to equal 1.96, but since that's a decimal, we'll approximate this to M being second order. Okay, so M is second order. So now I'm going to just plug in my numbers here, right? So I'm going to say, okay, well, our rate, I'll go back to the red pen. Our rate is equal to the rate constant K times the concentration of NO2 to the second power times the concentration of CO to the zero power. But as I said, anything raised to the zero power is 1. So I can reduce my rate law to the rate equals the the rate constant K times the concentration of NO2 raised to the second power. And that, folks, is the final answer of number 1. So number 1, the rate is equal to K times NO2 raised to the second power. Alrighty, now I can do number 2. So all I copied down from number 1 on the previous slide was the final answer, which was the rate equals K times the concentration of NO2 raised to the second power. Okay, so now I'm going to solve for K. So K equals the rate over the concentration of NO2 squared. Okay, so let's plug in some numbers now. So K is going to equal, I'm going to do trial 4 here because we didn't use trial 4 on the previous number. So I'm going to do trial 4 here. Okay, guys, so we're going to have 0.033 molar seconds divided by 0.4 molar squared. Okay. Remember, guys, that reactant constant K can change units, so it's super important that you write your units down here. Okay. So let's take a look what this is going to be. All right. So when I get 0.4 squared, it's 0.033 molar seconds divided by 0.16 moles squared. Okay, so that's going to, one of these m's will cancel out when I divide these out. And our rate constant K is, I get 0.21 m to the -1 s to the -1. Or another way to write this was our reaction constant K for this particular reaction is 0.21 per molar per second. Again, per molar per second. So if you wrote it like this, I'd also accept it. So it'd be per molar seconds. Okay, so that is our rate constant K for this reaction. And guys, that's the end of today's video. So big summary of what we talked about. In order to determine the rate law of a particular reaction, you first need experimental data. In order to determine the reaction order for a reactant, you need, guess what? An experiment. In order to determine the rate constant K, you need, guess what? An experiment. So with that being said, guys, we need experimental data in order to find these things. Once you find the reaction order of your reactants, you can then find K, okay? And of course, you can then, once you get, let me rephrase that. So once you find your reaction orders of your reactants, you can write the entire rate law. And once you have the rate law, you can then find your rate constant K for that given chemical reaction. With that being said, guys, that's the end of today's video. If you have any questions, shoot me an email.